I am Patrick Reynolds. I run the Git Infrastructure team at GitHub. My profile picture has a tiny red hat. I'm wearing this so that people will recognize me, but now I'm not. Today I'm going to talk to you about how our team runs a scalable, reliable Git service for GitHub. The Git Infrastructure team runs the Git service at GitHub. We operate two layers of GitHub stack. First, we run the file servers. We've got hundreds of Git file servers, each one with big SSDs, lots of CPUs, and a few 100,000 repositories. Above that layer, we have proxies. We have proxies for HTTP and HTTPS. We have a cluster with proxies for SSH, a cluster of proxies for subversion. And these are the proxies that you hit when you use your Git or subversion command line client to get to your repositories. And then finally, we have internal APIs that the rest of the GitHub stack uses to get to repositories that the github.com, the website, is built on. Our job as a team is to run that service scalably and reliably. We've got 38 million repositories. We've got more than 36 million gists. Those numbers keep growing. The servers we run, the Git file servers, they respond to over 1 billion repository touches per day. So some of these are simple things like list the branches or fetch the README so that we can draw the front page of the repository. But a lot of them are fetches, pushes, clones. They're heavy work. It's our job to handle all of that traffic and to handle more and more each day. And it's our job to make it reliable. The service has to be up. The service has to not lose data. And it has to respond to every one of those requests in a timely fashion. The focus of my talk today is a system called Spokes. Some of you may have heard of this previously as dgit. The name is now Spokes. Spokes is the distributed system that maintains the Git repositories on those file servers. Spokes is a big, big part of our scalability and reliability story for the Git service. We've been working on Spokes for coming up on 2 years now. And at this point, we've moved every repository, every wiki, and every gist so that it's stored in Spokes. The goals that you see here, these are the goals that we set out, some of the goals that we set out when we decided to build Spokes in the first place. These are things that the previous version of the Git service could not do, and that Spokes needed to, and now can. So briefly, anytime one file server is down, users need to not notice that. There's no impact. It can't be publicly obvious when a server goes down. If there are two servers down, we minimize the impact, and I'll get into more detail on that. Spokes needs to automatically balance disk space and CPU load so that there just aren't hotspots in the cluster. If there are hotspots, they need to be self-resolving. Spokes needs to automatically resynchronize and repair after any damage. So failures are inevitable. After a failure, there's work to be done. Spokes needs to figure out what that is and do it automatically. Spokes needs to provide horizontal scaling, meaning we've got this tier of GitHub stack. Anytime we need more capacity on that tier, I don't want to do anything other than provision a file server. Spokes needs to do the rest automatically. Maintenance operations, things like reboots, taking broken servers offline for repair, taking old servers, aging out old servers permanently. All of that also has to have no user-visible impact. And then finally, we want to deliver all of these benefits for GitHub Enterprise too. It's nice to have this for github.com, the website. We want to share it with our enterprise customers. The rest of my talk today is about how Spokes meets these goals. There's a time-tested way to achieve reliability in a distributed system, and that's replication. Just make copies of stuff. If your stuff, whatever it is in only one place, then it's only as reliable as whatever that server is. That server goes down, it takes your content with it. So in Spokes, we make 3 copies of everything. Spokes is application-level replication for Git. We make 3 copies of every repository, every wiki, and every gist. So concretely, what this means is when you create a new repository, we actually create 3 physical Git repositories on disk on 3 different servers. And every time you do some sort of change to that repository, a write, a push, opening or closing a pull request, we write that synchronously in 3 places. We update all 3 servers together. Now, this is a little bit unusual. Most distributed systems do their replication at the level of entire disks or entire servers. So, for example, RAID says, make a copy of this entire disk. If one disk goes away, we can rebuild it. And MySQL typically replicates entire servers. Previously, our Git service used a product called DRBD. That also replicates entire servers. Spokes does not here. So Spokes is replicating individual repositories, which gives us enormously more flexibility. Here's how that works. So every write goes to all 3 repositories at once. And as long as 2 repositories accept the write, they come up with the same answer after the write, we consider it a success. Every read goes to just 1 repository. There's no reason to replicate a read. Which means that as long as any one of the 3 copies of something is up, reads can still succeed. Now, I've said the number 3 here several times. We make 3 copies. That's not hard-coded. That's a policy choice. We chose 3 because it's the smallest number of replicas that can tolerate 1 failure and still commit writes. But if we had reliability requirements that said 4 copies, 5 copies, 6 copies, obviously that's a thing we can do. So the first and probably most important goal for Spokes was surviving failures. We have server failures a lot. We run enough servers that fairly regularly something will happen with the kernel or the hardware. So even in the 6 months that we've had most and then all of the site on Spokes, we've had loose memory chips, we've had bad motherboards, we've had weird deadlock in the kernel file system driver. And these all, I hope, weren't visible to you as our users. Because when the file servers go down, we're able to route traffic somewhere else until they can come back up. Now, when GitHub started out, and I think where a lot of sites start out, is when you have a small number of servers, you can pretend they don't fail. And you can just apologize nicely when they do. When you have a few more servers, you can spend lots of money, and you can buy the most reliable hardware you possibly can, get everything redundant disks, redundant networking, redundant power supplies, ECC memory. And for a while, you can keep pretending that failure isn't real. But when you've got hundreds of servers, the illusion breaks down. I mean, even we have expensive, very reliable servers, and they still do fail. We lose servers enough that this matters. You can see this here. This is a screenshot in the middle of this slide. That's a screenshot from the GitHub status page from last December. This is the old file server cluster, not Spokes. And so reading bottom to top at 3:03 p.m., we are troubleshooting an issue affecting a small number of repositories. Then 17 minutes later, we are continuing to investigate the issue. Less than 5% of repositories are affected. And then finally, 8 minutes after that, everything is operating normally. Now, on this old cluster, less than 5% of repositories, that's code for a file server has crashed. We no longer have status messages like this. File servers, when they crash, we no longer have to tell status. But you can see here, it took 25 minutes. It was 25 minutes of status just because one file server crashed, which is not supposed to be a big deal. That's how long it took for a human being to notice, to manually fail over, for the server to reboot, for us to verify that everything was healthy, and then to notify the world that we're back to normal. Now that we have 3 copies of everything, we just route around failures like this. We send every request to the best server for handling that request. And so the question is, how do we know what's best? We start with a list of replicas. So as I said, every repository is replicated in 3 places. We filter that replica list according to which replicas are online, not overloaded, and up to date. And ideally, out of this filtering step, we still have 3 servers. Almost all of the time, we still have 3 servers. But if we don't, we have to have at least 1 or 2, depending on whether we're doing a read or a write. The next step is to sort that list by some utility function. So we just have a function that captures what we believe will be the best server to handle that request. And there's some randomization in it so that we can do load balancing. At the end of that, we've got a list of all of the servers that we believe are capable of handling the request, sorted by which ones we believe will do the best job of handling the request. And for reads, we direct the read. So and a read here includes a fetch or a clone or retrieving one file or retrieving a diff and so on. For any read, we try the first server in the list, the next server, one at a time. Ideally, the first one should succeed. With a write, we send it to all three. And as long as two of them come back with the same answer, yes, I've accepted this write, here is the result, then we consider the write a success, and we tell the client that the write succeeded. This still raises the question, how do we know which servers are online? That's part of the filtering step, is online replicas only. And the way we do that, we have a failure detector. Specifically, Spokes watches real application traffic. It watches every internal API call. It watches every fetch, push, clone. And anytime we see 3 failures in a row to the same server, we flag that server as offline. As soon as we see a single success, we mark the server back online. Now, it's important here that we watch real application traffic. So a simpler solution would be just to have heartbeats. But heartbeats aren't very useful. They don't test much. So for example, the simplest heartbeat is ping. And all a ping is actually testing is, does the remote end still have a kernel with a working networking card? Because you're not even going to user space when you're pinging something. All you're asking is, do you have an ICMP stack? Which is not a great approximation of, can you handle application traffic? Next level up, maybe you have a heartbeat that makes TCP connections. And in fact, we have an internal API called online. And all this does is make a TCP connection and get back true, the serialized value true. And again, you're still not testing very much. You can design better and better heartbeats. You could design a heartbeat that says, here is a repository that has to be up. And we send ghost traffic to it. And you know what the right answer is for this repository. In fact, all you're still really testing is that repository. There are still failure modes like a disk is down, or the Git binary is corrupt, or a system library is gone, where you've got failure modes that none of these heartbeats are going to detect. But the thing that can detect, does application traffic work, is the application traffic itself. So our failure detector is based entirely on that. We do use heartbeats for 2 things. Once we've marked a server offline, we stop sending it application traffic. So the only way to know when it's come back online is with a heartbeat. And so the heartbeat has a prospective, yes, this is now responding to TCP connections, and then we go back to using the application traffic to say, is it really back online? The heartbeat also pulls the CPU load for the server. And I'll come back to that in 4 slides. That's important 4 slides from now. Now, requiring 3 failures to detect that a server is offline still means that 3 user-visible operations failed. And our goal here was 0. So what we have, as I said, the routing process that filters and sorts the list of replicas, the output of that is still a list of replicas. Even though we only need 1, we provide 3. And so everything that performs reads, fetches, clones, and all of the internal APIs that look like reads, they know how to fail over quickly. And so for 1 second, they'll try to connect to the first server. And if that doesn't work, try the next one, try the next one. And so as long as 1 server is up, you'll find it within 2 seconds. And this is basically not user visible. One key fact about our failure detector is it actually maintains a separate list of failed nodes from the point of view of each client. Now, why do we do that? When one file server is offline, so here you can see we are sending application traffic to DFS4. Sorry, take a step back. The nodes on top here, these are the clients of our internal API. And the nodes on the bottom, these are the file servers. And in red, I've shown the arrows that seem to have detected failures. And so if you look at this, you can say, well, it looks like DFS4 is really down, because every client is unable to get to file server number 4. And that's the truth. They've all detected the correct truth. So we could, in this case, have a single master list that says file server 4 is down. But not here. What happens if one of the clients is faulty in its implementation of the failure detector? Or if one of the clients loses access to the network that goes to the file servers, but can still report to the failure detector that it thinks every file server is down? You don't want to amplify this and say, all front ends should now treat every file server as down. And so we have an individual view for each of the clients. This is quadratic. We send a lot of heartbeats for this. And so we've just made the heartbeats cheap enough that it doesn't matter. Now that you understand how Spokes' failure detector works, let's prove it out with a demo. The abstract of my talk said, watch as we induce failures, and ideally, no one notices. So here goes. First thing I'm going to do, let's make that window a little bit bigger. All right, we're logged into production here, and I'm going to find servers that are not in the middle of long-running clones. And I'll explain why in a minute. Let's reboot DFS 1174. And just for fun, that's a typo. 1174. Let's get a console for 1174 so that we can watch, so that you know that this is not fake. This takes a moment. Sorry, it's loading a JVM. All right, there is a client. It's got a root prompt. And now we will, this being GitHub, we reboot things with chat ops. So gpanel host reboot GitHub DFS 1174. The whole fully qualified name. And Hubot wants me to say a magic word, just so that I don't do this by mistake. It's not a security measure. It's just a typo measure. Take this moment and make sure you're rebooting the right thing. OK. Comes back, rebooting host. Oh my gosh, check the status page. No signal. That's our console. And we could now just sit here and watch for 5 minutes as this massive server goes through its power on self-test. But you get the hint. So we're going to go back to chat ops. And I'm going to graph. This is our not our heartbeat, sorry, our failure detector. This is the RPC calls. Oh, look at that. That's a lot of them failing, which is exactly what we want to see. This is a measure of actual application traffic that is failing off of DFS 1174 and onto something else. There's a massive spike here. This is the graph that we base our alerts on. Because you can see it's a very clean graph, except that suddenly DFS 1174 has this huge spike of hundreds of requests that suddenly had to fail over. So everything is working as intended. And fingers crossed, I'm not looking at the status page. But I'm going to go back to my talk, and we can check in on that later. All right, and I had an animated GIF in case the Wi-Fi was flaky, but actually I'm glad I could give the real demo. So now let's revisit the first 3 of our goals. First, what do we do when a server is down? Is there any user visible impact? Well, I hope not. When a server is down, our failure detector notices it, and we route traffic away from it in real time. Any traffic that was supposed to go to that server just fails over to the other replicas quickly, so that no user visible operations fail. And because we're replicating at the level of repositories, this doesn't even create hotspots. So if we were replicating entire servers, when you take one down, it would have exactly 2 servers available to pick up the slack. But because we're replicating at the level of repositories, the rest of the cluster now proportionally picks up the slack. So we haven't created a hotspot. So indeed, this is no impact. And then writes go to all healthy servers. So because we've taken one down, everybody still has at least 2 copies. All the writes are still succeeding. Our next goal was that when 2 servers go down, there's minimal impact. And so the best case scenario here is 2 servers go down in the same rack, and there's no impact at all. And that's because we treat racks as availability zones. Servers within a rack have somewhat correlated failures. You can lose power to that rack. You can lose network to the rack. Somebody really strong could come and tip over the entire rack, whatever it takes. Those servers, the servers in the rack are somewhat more correlated than servers in separate racks. So we've built in this assumption that we can lose an entire rack and there's no user impact. But if we lose 2 servers in 2 different racks, Right now, it's about 1/100% of repositories that are now read-only. They don't accept writes until at least one of those servers comes back up. And interestingly, that percentage actually drops as our cluster gets bigger and bigger. That's given the current size of the cluster. That's a tiny percentage. In fact, it's the best that you can do for tolerating 2 concurrent failures in a cluster of our size. And the good news is we have not yet lost 2 servers at the same time. We always bring one back before anything else fails. The third goal we can look at now is balancing CPU load. And this turns out to be really easy. You treat, remember I said 4 slides from now? This is 4 slides from now. You treat any server with an unusually high system load as offline. Even though the server is still present, you just stop routing traffic to it. You proportionally spread that traffic over the rest of the cluster until that server can work through whatever that backlog is. And previously, we used to fail servers in the old file server cluster. We used to fail servers just because they were overloaded. They would hit a system load of 80 or something, and they would start thrashing, and they would be unable to keep up with a load arriving on that server. Now, when a server hits a system load of 80, we just stop sending things to it until it works through its backlog and it stops thrashing. This feature also is a crude way to allow a single repository the capacity of 3 full servers. So it fills up one server, and it spills over onto another server, and it spills over onto another server. We have a small number of very busy repositories that do actually do that. Shifting gears a little bit, what happens after a downtime and what happens after a failure? So if a server is offline for a while, we're accepting hundreds of writes per second, not to an individual server, but across the cluster. But that still means that if we're down for minutes, we have dozens or hundreds of writes intended for that server that didn't go to that server. So this is standard replication question. How do you catch it back up after it recovers? And then after a failure, that server is not coming back. After a failure, you've got to replicate everything that was on a server that failed. So it had hundreds of thousands of repositories. Now every one of those repositories is down to 2 copies. We have to create a 3rd copy somewhere else. 2 copies is OK. The problem with 2 copies is any other failure in the cluster, unless it's in the same rack, any other failure in the cluster is suddenly going to be user visible. So when we've got repositories down to 2 copies, we need to get them back up to 3. And the way that we do that is a recovery process that's based on 2 programming ideas, goals and repairs. Goals are properties that are supposed to be true. They're not invariants. They are properties that sometimes aren't true, but they're properties that are supposed to be true. And we express them as SQL queries. And these SQL queries return a list of repositories for which the goal isn't true. And in a moment, I'll get into some specific examples. Repairs are paired with goals. For each goal, there is a repair, which is a small Ruby program that can make that goal true if it isn't already. And so anytime we find a goal that isn't met, we schedule the appropriate repair using Rescue, which is GitHub's job queue. It's open source if you want it. All of our goals are checked every 2 minutes, and then the repairs run asynchronously after that. So here are 3 concrete goals. The replicas of every repository are supposed to match. So if you make 3 copies of things, they should have the same contents. And we check every 2 minutes, which sounds really expensive. But in fact, what we're checking is checksums. Whenever we write to a repository, we update a checksum. So what we're looking at is, do the checksums of the 3 replicas match? And anytime that they're not, we schedule a repair. And the repair just says, copy the bits from a replica that's healthy to the replica that isn't. Second goal, we have to have exactly 3 copies of everything. There are cases where we have more than 3 copies. There are certainly cases where we have fewer. And the repair knows how to delete the extra copies or create the missing ones. Finally, we have as a goal, are all the disks balanced, which looks at how full all the disks are. And if there's more than 10% between the fullest disk and the emptiest disk, we move replicas around. And this is another great flexibility of replicating at the level of repositories is it's granular. You can move a little bit from the fullest server to the emptiest server, and you just keep repeating that process until the disks are sufficiently balanced. So why do we do recoveries this way? There's a member of my team who likened this to putting on a blindfold, throwing a handful of needles into a haystack, taking off the blindfold and just sifting through the entire haystack looking for needles. And he's not wrong. This is inefficient in that at some point you knew you had a handful of needles, and you know that you're the one throwing those needles, that there is a point in the code where we could detect the error conditions, and we could try to schedule the right repair at that moment. But we don't. And so this slide is how I justify why. First, this goal-based programming, it's decoupled in code. So keeping the repair mechanisms separate from product code makes both of them simpler. Our team, the Git Infrastructure team that built Spokes, didn't write the product code. There is 9 years of GitHub product code that runs the website. We didn't write most of it. We didn't read all of it. But we still have to, we've introduced new error paths into that code. And so rather than go back and put rescue statements in all of that code and try to catch those errors and repair them in real time, what we know is what a healthy repository replica looks like. And so every 2 minutes, we say, are they all healthy? And if not, we fix it. And that means we don't have to go through this entire much older code base that's maintained by other people. And even if we did go through all of it and get it right, then we'd have to maintain all of those error checks forever in code that doesn't really belong to our team. Second is it's decoupled in time. When a failure happens, turns out to be a lousy time to try to fix that failure. The failure probably happened because a server was down or was overloaded or a process crashed or something timed out. This is not a good time to say, well, let's copy some more bits around. You're probably going to make, either the system is unavailable enough that you can't run the repair, or it's available but overloaded, and you're just going to make the problem worse. So we don't. Instead, we have this process that 2 minutes later comes and says, what's broken, and can we fix it now? And if we can't, then 2 minutes later, it's still broken, and you ask again, and you reschedule the repair. And so you just automatically keep trying these repairs until you can, until they can succeed. And they're throttled as well. If there are too many repairs for a 2-minute period, they'll still be broken 2 minutes later. That repair will get rescheduled. Finally, this code is reusable. So you can tinker with the goals to accomplish maintenance tasks. Let's say we wanted 4 copies of everything. We set a goal that there are 4 copies of everything. Nothing else changes. We don't have to write the scripts to make those copies. We just say, now there are supposed to be 4. And the task that creates more copies of replicas just goes and does it. It will probably take days. We have a lot of repositories. We could also we could trigger a repair. If you zero out the checksum on a replica, then the code that says, are the contents identical, will say, no, they're not. It'll recalculate the checksum. It'll copy the bits around, whatever it takes. So let's revisit the rest of the design goals and see what we've achieved. We had as a goal balanced disk space. And as I said, the way we do this is we set a repair goal, which is distinct from our design goals. We set as a repair goal, disks are balanced. And we have a repair process that moves repositories. So yes, we did this. Another design goal, we automatically resync and repair after any sort of server level failure. And yes, we created a repair goal that said repository contents, their checksums are the same. They have to be unanimous. And we just have a Ruby program that uses git fetch and rsync to make that so anytime that it's not. We wanted our maintenance operations to have no impact. So specifically, reboots and retiring old servers, that's supposed to have no impact. We could, naively, we could just treat every reboot like a server crash. And we could treat every planned retirement of a server like a failure. We don't. It's close, but we don't. And the reason for that is the same reason that I asked which of these servers don't have long-running operations on them. Because the one thing you can't fail over is a fetch or a clone that's already in progress. So if somebody is spending 12 hours downloading cyanogen over some very slow link, you don't want to, 10 hours into that, say, now's a good time to reboot the server. Because they're going to have to start again from scratch. And so it's just rude to have a planned maintenance that involves cutting off these long-running downloads. So instead, we flip a bit that says, this server is going away soon. Don't start any new work on it. Similarly, with retiring a server, you set a bit on that server that says, this server is going to retire soon. Evacuate all of the replicas from it in a controlled fashion. And so this gets back to the goal-based programming. You just set a goal that says the replicas on the server that's going away, they don't count anymore. So now there are only 2. If you need those, you can go get them. But in terms of do we have 3 copies, those don't count. We have only 2 copies of all of the hundreds of thousands of repositories. Now it's time to fix them. And then you give it a day, and it makes a 3rd copy of everything. And now the server is empty, and you can get rid of it, and definitely nobody cares. The reason, as I said, the reason you don't want to get down to 2 copies of things is that's healthy, but it doesn't tolerate another failure. You don't want to risk having that failure during the day that it takes to rebuild the server's replicas somewhere else. You don't want to take a second failure and have things become unavailable. Now, since this slide, thematically, this slide was about rebooting and it not having an impact, just for fun, let's go see if the DRAC came back up. We've got to restart the console. So instead, let's go here in chat ops. There's no data there because nothing has failed in the last 10 minutes. Let me graph the last 20. So there's the previous spike. You can see DFS 1174 was down for 3.5 or 4 minutes, but now it came back. I mean, there are no more failures to it. There's nothing more to route, and we're just flatline. All the servers are healthy again. So that's good news, doing that demo, and it didn't break things. Back to the talk. So the final technical goal here was horizontal scaling. We want to be able to add more CPU or disk space and have spokes just automatically take advantage of it. And step 1, add a server. There is no step 2. Since spokes automatically balances the disks, when you add a server, that server is empty. And that doesn't satisfy the goal that disks are roughly equally full. And so now we just start pulling repositories from every other disk and putting them on that empty one until the levels meet somewhere in the middle. CPU sort of goes along with that. As you move replicas to that server, you are moving CPU load to that server as well. If it's not perfectly balanced, then you have the ability to spill over if some other server gets busy. But in fact, the last step of taking advantage of a new server, of scaling something up in spokes, is setting the bit that says this server is online. And then you just forget it. It takes care of the rest from there. And yes, this works in Enterprise as well. So if you've heard of Enterprise Cluster, spokes is how we manage all the file servers in Enterprise Cluster. All the same technologies. Lessons I hope that you take away from this talk. 1, replicate everything that's important. This is basic. If you care about data, make more than 1 copy of it somehow, whether that's RAID or DRBD or database replication or building your own bespoke application-level replication solution, whatever it is, just make sure you make enough copies. De-emphasize individual servers. So if you've built a distributed system and you can point to one server and say, I will get woken up in the middle of the night if that server fails, your design isn't right yet. Application traffic is better for detecting failure than heartbeats are. Heartbeats don't test anything important. If you're trying to answer the question, can this server respond to application traffic, the best way is to look at the return codes from actual application traffic. Similarly, when you're trying to write error handling code for a service, sometimes it's better to focus on the properties that are supposed to be true rather than every possible way that those properties could become false. Focus on, here's what it should look like, and when it doesn't, here's how we get there. And that's one check and one state transition, rather than revisiting your entire code base and trying to find every error path. And finally, if this talk was interesting to you, and I hope that it was, we've got a couple of blog posts up about it at githubengineering.com. Lots of other blog posts too, but 2 of them specifically on spokes. And that's the end of the talk. Thank you for your attention. I'd be delighted to take questions. Sorry, is it only what?
Will even the biggest repo only ever be on 3 servers, or is there some other?
So far, we've never needed more. But sorry, yes, I can hear the question, but I'll echo it back. His question was, do we ever need more than 3 servers to handle our very busiest repositories? And the answer right now is no, we don't. Our file servers are pretty well spec'd, and no more than a half a dozen or so of them even need 2 servers, let alone more than 3. But we could set a replication goal. If one of them needed 5, we could set a replication goal that that one repository is in 5 places, or is in 6 or 7 places. There's also, we have the spillover mechanism when some server gets massively overloaded. We also already today can flip a switch for individual repositories that say, just load balance this one always. So that step that says find the replicas, filter it, sort it, you can put a random number in the sorting routine so that reads go randomly to 3 copies. And you can even weight it so that if one of the servers happens to be bigger. And this works really well. That's for 3 so far. We could certainly go higher numbers later.
So if you're in the repair mode where one of the goals that you wanted, such as 3 replicas should be present for every repository, is not met, and you're in the process of actually making a copy 2 minutes later, how do you ensure that there is an invariant that the source that you're copying from does not get into an error state during the process of the copy? Because there must be a finite amount of time that it takes to perform that corrective operation, during which time that source that you're copying it from, which was canonical and true beforehand, could now go down. Do you have ways to prevent that sort of stuff from happening, where the repair mechanisms themselves could have failures in them?
Yes, absolutely. So by default, the repairs are lock-free, which means they are intentionally copying from a target that could have a failure or even accept a write, and you sort of get halfway through that write. What happens is at the end of a repair, we recalculate the checksums atomically on all 3, and if they're still in disagreement, then we're going to do another repair. And after a sufficient number of failed repairs, then we actually take a lock and we say, no changes until this gets properly repaired. Up front? Sorry. Oh, she's taking the microphone to the back. I guess he'll be next.
Just a quick question. How far away have you been able to put your clusters and have them remain viable?
Can you speak up? The speakers are all facing away from me.
How far away have you been able to place your clusters and have them remain viable? Like,
how far out of the what?
How far, like rows, how many hops within your network, that type of thing?
Network latency?
Yes.
Right now, they are all in the same region, and so latency is measured in small numbers of milliseconds. Spokes is ongoing work, and part of the ongoing work is dealing with much higher latencies so that we can put them in other states or other countries.
Yeah, you mentioned that you were considering this architecture for GitHub Enterprise. Do you have...
Not considering it, shipping it.
Shipping it. So do you have a roadmap for that, or what challenges have you run into in importing that over?
I mean, I don't have any timelines to share today, but yes, once we get it working for github.com, the website, I expect the same technologies to be available almost immediately in the next release of Enterprise.
Okay.
One over there. I've got 6 seconds left.
Is 3 like really a magic number, like the checksum error? What if you had 3 checksum errors and you lost like the one good checksum, or will that just never happen in your experience?
I'm sorry, do you mean keeping 3 replicas or 3?
Well, you have 3 replicas. What if you had a checksum error on, what if all 3 checksums were out of sync, or does that just never happen?
That very, very rarely happens. So what we do actually is, after any operation, we have what the definitive checksum is. So when they're not unanimous, we still have one that all of the other copies are supposed to agree with. And so as long as the definitive checksum agrees with one of them, the other 2 can catch up to it. It's not always a majority vote. There are cases where it's these 2 return an error and this one returned a success, for example. 3 turns out to be enough. We very rarely have to step in and manually repair anything. And when we do, the manual repair isn't repo surgery. It's just, let's look at what the differences are among these 3 and say, this is the one they should all look like.
If you had 6 months of uninterrupted work with Spoke, what features would you add?
Of uninterrupted work?
Uninterrupted work. No bug reports, no interruptions, not even a Slack message.
That's
and
not
no
how
red
my
hats.
job works. I'm the manager of the team, so I'm constantly interrupted, actually, by managing the rest of the team. If I had 6 months worth of work, I would focus on, actually, the network latency question. All right. Thank you, everybody.